Hello, I'm Richard Gibson, and this is the first video in a series of tutorials about distributed acoustic sensing, or DAS. DAS is a really cool and a very powerful technology that's being used more and more frequently in many applications such as oil and gas production, geothermal energy, and a number of other areas in the geosciences. Each video will be covering a different topic related to DAS, and in this first episode we'll start from the basics. We'll learn how a DAS dataset is collected and what physical quantity it measures. This will give us a solid foundation for the other tutorials that will begin to explore fracture models and how they relate to observations from DAS data. The goal is to help you understand DAS data in general, but also how data sets can provide very powerful insights for monitoring of hydraulic fracturing. So let's get started. Here I show a simple schematic illustration of a well with its vertical and its horizontal section in the gray line. And then in the light blue line, we show a fiber optic cable which would be installed in the well environment. In some cases, the fiber optic cable is installed permanently in the cement layer outside the casing in the well. Other times that fiber will be deployed temporarily in the well. For example, this might be during the specific time period of a given hydraulic fracturing project. The final item that we show here is the interrogator unit, that central component that acquires the data. And the first step is that interrogator includes lasers, which generate light pulses which travel downwards along the fiber optic cable. Importantly, however, that interrogator unit, the same device, records returning backscattered energy that is reflected from or scattered by heterogeneities or scatterers located in the fiber optic cable. And here in the illustration, I showed just a couple examples of positions of scatterers for illustration or for visualization. Really, the scatterers are just minute heterogeneities within the fiber optic cable located everywhere along its entire length. So the interrogator fires off that laser pulse. It travels downwards along the fiber optic cable. And again, when it hits those scatterers, some of that light energy is backscattered and returns back to the interrogator, which measures it. Now, even though, again, the animation emphasizes only that pair of scatterers, this process takes place everywhere simultaneously along the entire length of the cable, so that we are sampling the entire fiber optic cable, which could be tens of kilometers in length. So again, we've got this returning light energy coming from everywhere along the cable. So how do we actually use that information to learn about motion of the Earth in that, which is in the locations of that fiber optic cable? Well, again, we go back to another simple schematic. And so here, again, we have our interrogator unit generating a light pulse traveling all downwards, all away from it towards the end of the fiber optic cable. It will encounter heterogeneities or scatterers, like I'm indicating with these reddish, brownish colored square units here. And when the light encounters those, again, part of its energy is returned or scattered back to the interrogator unit. And that energy takes a certain amount of time to return to the interrogator. And what's important here is the difference in time for those two pulses which are backscattered from each of these individual scatterers. It depends on the distance between the two scatterers as well as the speed of light. So now the important point. Imagine that we go onwards in time by some small amount dt, and the fiber optic cable gets a little bit longer. Again, maybe there's some motion caused by the formation of a hydraulic fracture nearby. When that fiber optic cable gets longer in this area, and so that the distance between its scatterers increases, then that it causes a difference or an increase in that difference in scattering times or times at which those signals are detected at the interrogator. And the interrogator then quantifies that increase in length as a positive value of strain of the fiber optic cable. So again, we choose positive signs here, positive signs for the strain to represent an increase in length. If at a later time the fiber optic cable gets shorter, the scatterers get closer together, that distance between them is smaller, so that the relative difference in the times at which the reflections are detected at the interrogator also decreases, and so it measures a decrease in length or a negative strain here. So then we also have some terminology, some relatively standard terminology, which is used to describe the data sets which are required by the DAS system here. First, there's the gauge length. That is the distance between the scattering points used to gauge or measure the strain, and we refer to that as DZ here in the illustration, but the common term is gauge length. There's also the location, or the reference location, for the point at which we are carrying out this measurement, and we'll refer to that as a channel location. Next, then, we can talk about some typical values for these parameters. The channel spacing itself is usually about 1 meter, but the gauge length is highly variable, can be set anywhere from 2 to 40 meters. So remember that the gauge length is that distance over which we measure the deformation or the lengthening or shortening of the fiber optic cable. That's really a good measurement of the spatial resolution of our outputs here. So even though it may seem when we have a spacing for our channels, our output locations as being 1 meter, you may think, I've got great spatial resolution of 1 meter, but really it's something closer to 40 meters since it is controlled by that gauge length. So this then raises the question, why would you ever choose that long value for gauge length? That gives you much lower spatial resolution. It's an issue of signal to noise. When you choose a small gauge length, any noise in the system, especially for very small values of strain, will give you a lower signal to noise ratio. So to get acceptable data quality, you may need to increase the gauge length. And in the end, the choice is a compromise between spatial resolution and a desired signal to noise ratios. The other sampling criterion to remember is that in time, and so we have the advantage of working literally at the speed of light with our laser-based system, so we can get thousands of samples a second. And so in this case, our maximum frequency content can be up to several kilohertz. Do note that the DAS system is able to accurately measure signal content at very low frequencies as well, under 1 hertz and approaching static values. To summarize, DAS measures strain, the relative change in length of the fiber optic cable. Sometimes it is reported or output as strain rate, or the amount of strain per time, but in the end, we're still just measuring that relative change in length of our fiber optic cable here. Secondly, the data set is very densely sampled both in space and time. We get measurements every 1 meter along a fiber optic cable, which is thousands of meters in length, and we do so thousands of times a second. In the next installment, we will look at some examples of low-frequency DAS data acquired during a hydraulic fracturing project, and we'll use some simple models of a hydraulic fracture as building blocks to start to develop some basic intuition to understand and explain some of the common observations. Thanks for watching.